Hello, my name is Natalia Janson, and I'm from the Department of Mathematics at Loughborough University. Today, I'm going to talk about a conceptual approach to artificial intelligence. I slightly changed the title of my talk. It now reads, Towards Explainable Artificial Intelligence Using Dynamical Systems with Self-organizing Vector Fields. And I would like to mention a small disclaimer that I'm going to paint a picture in very broad brush strokes. I don't have time for nuances, and of course there is a myriad of them. But everything I say will be supported by references, and I'm not including too many references in my presentation, but I'm happy to share these references upon request, if you're interested. Of course, everybody appreciates that modern artificial intelligence is hugely advanced. This has been widely discussed today, but it is not perfect because modern artificial intelligence, particularly the one in the form of neural networks, deep neural networks, suffers from some considerable issues. Some of these issues are listed here. One major issue is catastrophic forgetting, when new memories are interfering with the old memories and the system abruptly and quite unexpectedly and unpredictably forgets what it learned previously. A directly related issue is the inability of the so-called lifelong continuous learning, when the previously trained neural network cannot easily learn new data by just adding new information to the previously learned examples, because it needs retraining basically from scratch. So adding just a few new examples is very difficult currently. The first two issues are interconnected. Then another interesting limitation of modern neural networks is that they find it difficult to learn from a single example, more or less like babies, like humans. Obviously, neural networks have limited memory, and the topic of this talk is explainability. Modern artificial intelligence works very much like a black box, in the sense that we do not really understand how it makes decisions, how it memorizes, and we have very little control on how it operates. We don't understand how it makes mistakes, and it does. And because we don't understand how it is making these mistakes, we don't know how to understand how to eliminate these mistakes. So overall, because of the lack of this explainability, modern artificial intelligence cannot be fully trusted. Well, I'm going to focus on a proposal which is not entirely new, which has been mentioned, although not very frequently. What about building artificial intelligence, an artificially intelligent device, in such a way that it does exactly what we want it to do and does not have limitations of modern neural networks? And why don't we try not to patch the existing AI, but to design a new AI with prescribed capabilities and in such a way that individual cognitive mechanisms are controllable by tuning parameters? And above my slide, there is a famous quote from Richard Feynman: "What I cannot create, I do not understand," which could be paraphrased also: "What I cannot understand, I cannot create." So in order to create a device, we need to understand it. Well, making artificial intelligent devices would require the same engineering principles as making any other devices with prescribed functions. For example, to build an artificial flyer, we need to know what flying is and how it is achieved. If flying is directed motion above the ground in a controllable manner, we need to know By what mechanism can one stay above the ground and to move in a prescribed direction? So basically, we need to know the definition, exact definition of flying, the principle of flying, leaning on air, the method how we can lean on air to shape the wings appropriately and to move. And there's the whole discipline, aerodynamics, which tells us how to achieve flying. Making flying machines has been going on for centuries, and ultimately what we know now tells us that by simply copying natural flyers, birds, by replicating all their wing flapping and feathers, we cannot actually achieve a good, optimal, controllable flyer. Instead, we're making airplanes based on the principles of flying. And this brings me to the next question. What does engineering artificial intelligence require? It requires, by analogy, some definitions of concepts related to intelligence, such as memory, brain code, some code, cognition, and learning. The principles of memory formation, controlling behavior, cognition, and learning, and the methods to implement such principles. And it requires a separate discipline. Treat this as a joke, but my suggestion is that by simply copying nature, the natural intelligence in the form of neural networks, might not exactly allow us to achieve the goal of an explainable artificial intelligence. So let's consider, and of course this conference is devoted to a large extent to replicating neural networks, so treat this as a joke. But let's consider a slightly alternative approach. Let's take some inspiration from the natural intelligence, which is the brain, and an artificial intelligence, the best one which is available to us, which is computer. These two devices share one common feature, intelligence, although to different extents. They have similar functions. And people have been comparing the brain with the computer a lot. For example, the existence of some code in the brain was assumed. So we need to discover what code is controlling the behavior. I would like to argue that a discipline which might offer some answers to the questions which arising in the context of intelligence is actually available. It is the theory of dynamical systems. This is quite a respectable discipline, which goes back to 1880s, so it is about 150 years old by now. Roughly speaking, what does it study? It studies models of real devices, real systems, expressed as differential equations, and a speciality of this discipline, it's a very prominent feature which might not be appreciated to the full extent in applications, is the following. This theory allows one to handle equations which cannot be solvable analytically, which is basically all equations describing anything of interest in nature and among the devices made by people. This theory contains a toolbox for explaining the following interesting phenomena: evolution, oscillation, self-organization, pattern formation, catastrophes, and chaos. It is extremely multidisciplinary. It has a good track record of explaining phenomena in all available sciences. It was used to design new devices, and interestingly, at the core of this discipline is a behavioral code, although it is probably not known under this name. So for a physicist, a dynamical system is a device which has an important quality. It spontaneously evolves with time. Spontaneously means that its state, such as current, voltage in electronic circuits, or say heart rate in animals, or for example in a chemical reaction, concentrations in a chemical reaction, or maybe a pendulum and a grandfather clock. All such objects change their state by themselves without any interference from the outside world. The behavior of such systems is determined by their physical architecture, and such systems kind of know what to do next in any situation. And interestingly, the brain itself is very well recognized by now to be a dynamical system, although maybe not exactly a standard one. For a mathematician, a dynamical system is not a physical device, but a model of this physical device. And it should be a device evolving with time. The observable behavior of this device would be determined by the evolution rules or behavioral code known under a different name. And a few examples of dynamical systems used for modeling various phenomena are shown here. For example, a mechanical pendulum, an electronic circuit, van der Pol oscillator, a neuron model in the form of Hodgkin-Huxley equations. But generally, a dynamical system would have this form. It will be a collection of first-order ordinary differential equations. On the left-hand sides of these equations, there will be rates of change of quantities x1, x2, up to xn, the quantities which evolve spontaneously. And on the right-hand side, there will be some functions of these quantities. Now, how can we obtain this behavioral code for a device? If we know the device, if we know the architecture and the parameters of a device, we can actually extract a behavioral code of this device, which has a name, a vector field. So what do we need to do? Look at this pendulum. I'm not going to consider all details. I will just remind you about the principle. We collect all physical laws which could be relevant to the given process. These laws come in the form of algebraic or differential equations. We combine them with a count of the architecture of our device. We rearrange quantities, maybe change variables, but ultimately we present the resulting differential equation in the form of a dynamical system. And because most of such equations will not be solvable analytically, we adopt a geometrical approach, which was first proposed in the middle of the 19th century by Henri Poincaré. Look what we do. We look at the right-hand sides of our equations, and we establish that the right-hand sides depend on the actual values of x1, x2 state variables. So basically, if x1 and x2 correspond to some point in the phase plane diagram, then at this point, we can construct a vector whose coordinates are the right-hand sides of our equations. And this is called the velocity vector or phase velocity vector. For every new point in this phase space, phase plane, in my example, there will be a new velocity vector, and altogether, the full collection of velocity vectors is called vector field or velocity vector field. And this vector field determines what the system will do next from every possible state. So essentially, it is the behavioral code, only known under a different sophisticated mathematical name. And you probably remember that in neural networks, in artificial at least neural networks, memories are sometimes thought of as attractors. So attractors are created by this vector field. And the vector field has many features which are very useful, but perhaps which are not very well recognized, particularly outside mathematics, and are not very well appreciated. And these are, apart from being the literal behavioral code of our system, this vector field is actually measurable via modeling. From the first principles, it provides an intermediate level between the architecture, the physical architecture, and the observable behavior. And in fact, it determines all capabilities of the system, describes self-organization It is emergent property of the device which arises from interactions between the elements of this device. And interestingly, it is arising out of the architecture. So it is not like a computer code produced by a human. Anyway, let's go back to natural intelligence. We need to get some inspiration and understand some technicalities. Look at, say, a human or a cat or a cockroach. How do we know that this animal or object is intelligent? Well, we observe their behavior. Now, what is behavior? According to psychology, behavior in humans is movements of various parts of the body and speech. Now, who determines this behavior? Well, we know who: motor neurons in the body. Now, who controls motor neurons? Motor neurons are connected to the brain, and basically neural firings in the brain will ultimately control the motor neurons and the behavior. So if the brain is a huge dynamical system, then the brain behavior, the neural firings, are controlled by the vector field of the brain. So after making this chain of arguments, we end up with a conclusion that if we want to understand intelligence, we need to look at the vector field of the brain. Of course, you might tell me that this is not new at all. Everybody knows that the brain has been modeled as a dynamical system for a long time, and individual neurons have been modeled as dynamical systems. Unfortunately, this knowledge did not really help us produce good artificial intelligence. Why would that be? Well, that's because it was difficult to understand what intelligence is, and the attempts to produce intelligence were largely limited, to a great extent limited, to reproducing the natural intelligence, the brain, with various degrees of accuracy, and to hoping that maybe if we replicate a brain in a hardware accurately enough, this hardware will think like the brain. However, if we look even at the very simple model of a neural network, this is the Hopfield model, which is learning, we will see how nonlinear it is, because these functions g, j have this sigmoid form, highly nonlinear functions, and generally the whole model is highly nonlinear and also high dimensional, because to do anything useful, the neural network has to contain many neurons, and such equations cannot be solved analytically. And moreover, even if we look at this simplest model of a brain, very crude one, we can see that various processes are highly entangled. We know that in the brain or in the neural network, learning is associated with a spontaneous change of these connections Tij between individual neurons. This change in response to the changes in the behavior Xi, Xj. And then the behavior for individual neurons for Xi will be affected by the connections and also the behavior of the rest of the network. So it is a huge entanglement between various processes, the observable neural activity and the process of learning, which is not really observable. These Tijs, connection weights, are not so easy to observe. So basically, if the brain is not really explainable, then a neural network is also very difficult to explain, even if it is very simple and artificial. However, from the work in artificial neural networks, we can take some hints. If we consider a Hopfield neural network, consider its version when the neurons are not coupled. This is a big dynamical system of dimension m. So we illustrate a dynamical system only for 2 neurons, but we can mentally extend it to many neurons, to m neurons. At each point, there is a vector field, and without couplings, the vector field is very simple. There are no attractors here. These individual neurons are not doing anything spectacular if they're disconnected. However, if now we introduce couplings, and these couplings evolve during learning, what does this neural network do? It learns in response to training stimulus capital I, this one, As a result of learning, these connections Tij will change according to some complicated rule like that. And suppose after learning, the neural network develops a certain vector field. For a two-dimensional network, this vector field is illustrated here, where we have these red dots. These are attractors, which are usually associated with memories. So what hint can we take from this knowledge? Well, we know that during learning, connection weights change, which means the whole vector field changes. If the vector field changes, attractors change, and also other objects in the phase space change. After the learning finishes, connections are frozen and the vector field is frozen. If our neural network is trained well, then we will have a certain number of attractors coding memories, and generally the shape of the vector field will be good. However, the difficulty here is that the vector field of the neural network is evolving in a complicated, not really well predictable manner. However, let's try to use this hint. We can conclude that to be intelligent, our dynamical system needs to be evolving its own vector field according to some good rules. And let's come up with the idea of a dynamical system whose vector field behavioral code evolves spontaneously following some rules. So you see at the top of this box, we have a standard dynamical system where X is the state vector and capital A is the behavioral code, vector field. Now let's add the second layer to this system and assume that the behavioral code vector field A evolves according to its own inbuilt rule C. Now, if we know this rule, we will in fact make our system explainable, because we will prescribe this rule with our hands. We will design this rule C to specification. So, and of course, this rule should be nice in the sense that if this rule C is good, then memories will be imprinted on the vector field in a good, controllable manner. And these memories will be updated in a controllable, predictable manner. And there will be no spurious memories, because there will be no mechanisms for their formation and no catastrophic forgetting. By the way, this idea is described in the paper from 2017, our paper. Right, so let's consider the simplest evolution rules, C, which could ensure some very, very basic cognitive properties in our system. And this idea is borrowed from the idea of a memory foam. Suppose we consider a one-dimensional system, only a one-dimensional system. X is the state, and the system describes a potential V. So our system will be gradient, so-called gradient system, basically describing how a particle moves in a certain landscape. And suppose we're trying to make the vector field as the negative of the gradient of a certain landscape, and we allow this landscape to evolve according to some equations. And if the external stimulus appears at some point, it makes a dent in the landscape. If the new stimulus appears close enough to the original one, the existing dent will be deformed, but this dent will be a memory of a single stimulus, which will be gradually, continually adjusted. However, if the new input is far away from the original one, it makes its own memory. And you see it as completely explainable, predictable mechanism. And let's see how it works. Maybe I'll skip a less interesting part and allow you to hear that. So basically, we developed a four-dimensional system following this evolution rule for the velocity vector field. We fed this system some music, which I'm going to play now. I hope you can hear this. Mary has a little lamp. This music is performed by a human, which means it is not perfect. It contains some noisy data. In fact, these green dots will show us how noisy the data were. And we filtered out from this music some dominating frequencies at the given time moment. The data is very, very noisy. And after processing this data, music remembered, recognized, and memorized by our system is basically a cleaner version of the original one. Anyway, what else was done with this kind of a model? Some further work was done by the PhD student of Alexander Balanov, Daniel Gascoigne. I collaborated with Daniel and Alexander as basically an advisor, informal advisor for his dissertation. And Daniel applied this system in order to try to recognize colors when our system was watching cartoons. One was Futurama, one was South Park. We allowed our system to look at one spot on the screen when it was watching these cartoons for quite a long time. And the task was to recognize colors, to identify colors spontaneously. So this system identified quite a lot of colors. For example, for Futurama, it recognized some colors, and the system's idea of the colors present in this cartoon was developing over time. So from top to bottom, our time increases. Some colors, for example, red one, blue one, they were present from the very beginning. And some colors were adjusted or added later. So the system has been doing lifelong learning without catastrophic forgetting in a perfectly explainable, controllable manner. I need to be finishing now. For South Park, it was doing the same quite consistently. Now, if there are any mathematicians present during this talk, they will probably ask me, but Natalia, you can't just construct a new mathematical object without checking its mathematical legitimacy. Well, mathematical legitimacy or consistency of such a system in a simpler form was checked, was verified by Peter Claudon, with whom we published 2 papers. So all theorems for the existence and uniqueness of solutions are proved, at least for a simpler version of this model. And so this is done mathematically. So neural networks might be a special case, but I guess I don't have time to consider this. Is that if we really want to have explainable and controllable artificial intelligence, we could design it to specification, perhaps rather than trying to explain the existing neural networks, which are trying to mimic the already difficult brain. The proposal is to base such new intelligent systems on dynamical systems with plastic self-organizing vector fields. And currently this idea is only an abstract conceptual model, which waits for its implementation in hardware. So I'm going to finish now, and thank you very much. And I'm happy to answer questions if there are any.